Hello, and welcome to a new edition of H.E.L Explains with your host, Dr. Mario Toubes-Rodrigo. Today we are going to be talking about a critical parameter on the scale-up processes in bioreactors. Today we will talk about the volumetric mass transfer coefficient of oxygen, or kLa. Scaling up fermentation processes from small benchtop experiments to large industrial production is fundamental for the viability of bioprocessing industries. However, this transition is not straightforward. Maintaining constant product quality and achieving high yields requires a very deep understanding of various variables, with oxygen transfer into the liquid medium being one of the most critical. Nutrients are oftentimes limiting factors in our fermentations and bioprocesses, and oxygen is not an exception. For optimal growth, then it is fundamental that we maintain oxygen levels above a critical threshold specific to the organisms that we are going to be using. The oxygen transfer rate, or OTR, is defined by the equation OTR equals kLa multiplied by delta C, where delta C represents the difference between the saturation oxygen concentration in the medium and the actual concentration. And then we have this other factor, kLa. And kLa is not a single coefficient, but instead is made of other two coefficients. On the one hand, K sub L, which is the rate at which the oxygen transfers across the liquid-gas interface. And then we have A, which is the interfacial area available for oxygen transfer from the gas to the liquid phase. At the same time, K sub L and A are also going to be impacted by several physical, chemical, and biological parameters. For instance, the size of gas bubbles in our medium are going to affect the interfacial area, and these can be modified through sparging and through agitation, but also the duration that the gas is going to be in our medium are also going to impact the solubility of these gases. Additionally, kLa scales linearly with the amount of oxygen introduced into the medium. While increasing agitation can enhance oxygen solubility, it may also lead to higher shear forces that can potentially damage cells, especially if they are susceptible to these kind of forces. Other variables that affect kLa include the cell type, media composition, pH, cell concentration, antifoaming agents. The design and size of vessels also plays a fundamental role, making kLa prediction challenging and needing individual assessments for each bioreactor. Accurate kLa measurements enables better tuning of oxygen concentration, increasing process yield and ensuring growth that isn't hindered by inadequate oxygen levels. A proper characterization of the oxygen needs also prevents resource wastage associated with unnecessary high level of oxygen in our medium. In comparison to kLa approaches, traditional scale-up approaches often relies on geometrical properties, such as height-to-diameter ratios or steroid ratios. Power input per unit volume is also frequently used and is considered a good indicator of culture homogenization, mixing, and shear stress. This approach encompasses both agitation, mechanical power that we are supplying, and sparge gas, so the pneumatic power that we supply. However, given that sufficient oxygen transfer is critical for cell culture, focusing on kLa aims to maintain similar oxygen transfer rates across scales. Ensuring that our oxygen transfer rate, OTR, exceeds the oxygen uptake rate, OUR, allows for a more efficient scale-up process, resulting in comparable growth and production rate across the whole of the scale-up. As we can see, Understanding and optimizing kLa is pivotal for a successful fermentation scale-up. By accurately determining kLa, operators can fine-tune process conditions, balancing factors like sparging, agitation, and pressure. This leads to improved process control and reproducibility, from lab-scale experiments to a whole planned industrial scale production. That's all from me. Thank you very much for joining us. My name is Dr. Mario Toubes-Rodrigo, and I am the applications leader here at H.E.L. If you have any questions, if you have any comments, please come and talk to us. Thank you very much.